Okay, friends, good evening. Now, as you can see here, a thought about the radius of curvature. Now, as you know, for circular motion, we used to write the acceleration or centripetal acceleration. Okay, so here we are writing it as APN, means acceleration of the particle P, which is normal. That is nothing but centripetal force. And we can write the radius of the circle. See, we usually used to use this type of equation for circular motion.
Yes.
Okay, fine. Now you see the particle is moving in a curved path, right? Just like Earth's elliptical path. So in a curved path, as such, okay, as I have already explained to you, the curved path means what? That means now at any point the curvature is a part of a bigger circle.
Yes, sir.
I hope all of you know.
Yes.
So the radius, the radius of the circle of which the arc is a part of it.
Yes, sir.
Okay,
Yes, sir.
becomes the radius of curvature at that point.
Yes.
Yes. However, now the challenge to all of us is, supposing the equation of the curve is given like this. You can see here y is equal to 5x cube minus x plus 14. Okay, supposing the equation is given like this, 5x cube minus x. What is this? This is the equation of a curve.
Yes.
Yes. And now, what is its curvature? You can see that the curvature will depend upon the values of x.
Yes. Yes.
Now the distinction is the radius of curvature is r, as I have told you.
Yes.
The reciprocal of this radius is called curvature.
Okay.
The reciprocal of the radius is called curvature. Please remember. Okay?
Yes, sir.
Fine. So therefore, now the formula for finding the radius of curvature is this: 1 plus dy by dx square whole bracket raised to 3 by 2 divided by modulus of d square y by dx square. Right? So anyway, you just put a thought to this. This you can find it in, because this is something which you are going to use quite often in mathematics. Okay, so this is just for you to get an idea that if at all we are going to encounter issues involving the radius of curvature, this is the formulation that you have to use, and you are going to learn quite a bit about it in mathematics. Okay? And if r is given in terms of polar coordinates, then this becomes the formulation. And you can see here, rho is the radius of curvature, and k is called curvature. Rho is equal to 1 by k. And here an arbitrary equation is taken. Y is equal to 5x cube minus x plus 14. And here the solution is for what is the curvature at x is equal to 2. Okay, so therefore this was just differentiated and substituted, and finally we got the radius as 0.2526.
Yes.
Just a small exercise just to tell you. Okay, fine.
Sir, if r is the radius, then 1 by r is the
Curvature.
radius of curvature.
No. Only curvature.
Only curvature.
Only curvature.
Yes.
See, what is the curvature? You find the radius and take the reciprocal.
Okay.
That will give you the curvature.
Curvature.
Okay, so you will use those terms, at in appropriate context, that will be more handy than this.
Yes.
Okay. Now, well, I would like to discuss something here. You see, now a body is in motion. I have already discussed this at times. So, if I take an arbitrary body, so if it is also having translative motion and rotational motion, supposing it is having both. Okay.
Yes.
Now, if it is having both, then if I say this is particle P, now what is the velocity of particle P? If I ask you, so what is that? You can tell me what is the velocity of particle P? I said it is having both translatory as well as rotational motion. Okay. So what I would like you to infer here is, there is something called center of mass,
Yes.
right?
Yes.
Now,
Yes,
there is
sir.
something called center of mass, and what you have to now say is, this body that I have drawn is unconstrained. Unconstrained. Okay, that is very important. That is, no force is acting, no external force is acting on it, or it is not touching any other. If it touches,
Yes.
automatically, the contact forces will come into it. So
Yes.
it is like unconstrained. There is no constraint on this body. So in other words, it is a free body.
Yes, sir.
And if I say this is a free body in transit, and it is rotating as well as translating, okay, then and if you locate any point here, so predominantly I am locating 2 points. What is this? This is center of what is this? This is COM, or the center of mass. So,
Yes, sir.
so let us all understand this. See, understand the concept of center of mass. See, we introduced that concept called center of mass and said something more about it. What is that we told more about center of mass? Please.
It is the sum of all the velocities of the.
Loud. See, your reference was here. You don't know.
The velocity of the center of mass is equal to summation of all the velocities of the particles.
How is it possible? How you can tell like that?
Velocity of the center of mass.
What is it? And see, all these particles will have some velocities. See, then you are going to add up and say it is center of mass. No, that is not.
Velocity of center of mass.
No.
Center of mass is a unique point or unique point on the body, or which can be in the
On the body or outside, some
On-
unique point.
Okay, sir. That body, it moves, or it moves such that all of the mass is concentrated at that point.
Exactly. That is the concept. That is the concept. Understand? So center of mass is that point where the entire mass of the body
Mass of the system is
assumed to be concentrated.
Assume to be concentrated.
Yes, yes, sir.
So if you say the body is moving with velocity v,
Yes, sir.
only translation, it is moving with velocity v. That means how did we see now this? Supposing I say this body is moving with velocity v, not rotation. Okay, then how you can represent this body? The equivalent of this body will be simply a point.
Point.
Supposing this is the total mass, then I am just going to write this mass and say mass is this. And if I say it is moving a certain velocity in so and so direction, I am going to attach the velocity vector to this. Now here you see, I will use the word C for the center of mass, and I will use the concept VC.
Yes, sir.
And supposing you apply force to this body, then again you see what happens if you apply force to the body?
It will accelerate.
Relax.
It will accelerate. How will you represent it?
It can.
How will you represent it? Again, you will see, you will take F by M,
If by
Yes.
and you will get acceleration vector. You will get acceleration vector, and you will attach it to the center.
center of mass.
Yes, sir. Yes, sir.
This is precisely. This is how you present the waves. So therefore, if I say this body is translating as well as rotating, then it's for sure that the center of mass now has got velocity vc.
Yes, sir.
Now, center of mass has got velocity vc. Okay. Now, just understand this. No, supposing I say the center of mass of the body has velocity v. So, this one I am representing the velocity vc of the center of mass at this point. Then, if I take this particle p, okay, this should also be moving with the same velocity vc. Or any
Yes.
particle that we
Yes,
take
sir.
actually.
Yes.
Then only I am taking particle 1, particle 2. Okay. Then only the entire mass will translate.
Translate.
Yes, sir.
Is equal.
Translate.
Understand. So translator motion, what did we say? You remember one more statement I said? You associate velocity vectors with every point.
Should be.
If the velocity vectors at all the points at all instants of time,
Yes.
if they are equal,
Yes.
then we say it is translating.
Okay.
Or during an interval of time, if all the velocity vectors are equal, during that interval of time, the body is translating. But now, for the purpose of analysis, you can just represent the entire body as a point mass, and you can do like this. But frankly speaking, all these points will be having this.
Yes, sir.
This is
Yes,
one.
yes,
This
sir.
is one aspect. This is one aspect. Okay. Now what I will do, the same body, I will say it is only rotating and not translating.
Yes.
It is only rotating and not translating. Okay. Then what have you got to say about the velocity of this point and velocity of this point?
The magnitudes are same but
Same,
in
but
opposite
direction
direction.
is different.
Sir, but rotation about what?
See, now please, the same body, I will write it like this, same body, assume that the same body. Now I am just showing you the same 2 points. Okay, center P1 and P2. Now I am telling that this is rotating with omega, only rotation.
About its own.
See, I am telling, see, now you see, if you feel that, something more has to be told, then only you ask question. In this context, I am not telling you don't ask question. What I am telling you is now, imagine a body is rotating.
Yes, yes.
I am asking you what is the velocity of this particle P1. So what will you say? Please, everyone, last class we have discussed quite a bit of this.
The perpendicular star to the velocity vectors, intersection of point of perpendicular star to the velocity vectors of those 2 points will meet at points. That point we can consider is at momentarily at rest, and the points are rotating about it.
Excellent, excellent, excellent. So fine. I appreciate. And I heard a new voice here. Who is this?
Swarup, sir.
Why, good, sir. Thanks. So you see, that means now you have got something called as center of rotation.
Yes, sir.
You have got something called center of rotation. Okay. So
Yes.
you have got something called center of rotation. Okay. So I will just say, okay, this is the center of rotation, or this is the center of rotation. So therefore, you see, so this becomes one vector, this becomes another radius vector, and about this point, if you say this is the center of this one, then this point is rotating, this point is rotating. So therefore, now if I draw a vector from here, then the velocity vector, the linear velocity vector will be perpendicular.
Yes, sir. Yes.
So this becomes the velocity vector because it is rotating. Okay,
Yes,
because
sir.
it is rotating.
Yes.
Because it is rotating. Isn't it? And this becomes the center of rotation. Okay, center of rotation. This becomes the center of rotation. See, listen. Now you see, supposing, now gentlemen, I said the body is rotating, man.
Only rotating. Yes, sir.
Okay,
Yes,
so therefore, if I say the body is rotating, then I didn't say it is translating.
Yes, sir. Yes,
So therefore, there is no question of instantaneous rotation. It has a permanent axis of rotation.
yes, sir.
Correct? So this becomes permanent axis of rotation, and therefore this VT. Correct? Now just say, like, supposing this body is now rotating as well as translating. Body is rotating as well as translating. Okay, it is very simple. So if you say it is translating, then this will have this velocity. Okay, and if you say it is rotating, it will have this. And if you say it is doing both, then you will have the result.
Yes, sir. Yes, sir.
So this becomes what? The velocity of the particle.
Yes, sir. Yes, sir.
So what you should appreciate here is velocity of a particle now is a combination of the translatory velocity as well as the rotation, velocity due to rotation. And the important thing is the translative rotation. Okay, the velocity vector while it is translating is the same vector that is associated with any point. See, now here you see I said that is VC, and for this also I should write VC. For the center of mass also I should write VC. Hello, are you with me?
Yes, sir.
That is one person. That is one aspect. Now the other aspect that I want to tell is, if you now see that a body is rotating and translating in free space, just like Vishnu, there is a god called Vishnu and his Sudarshana Chakra. It keeps going taka 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 like this.
Yes, sir.
Okay, so it keeps moving. So now it is like a free body. Understand? There is no force acting on it. It is going by itself. It's not touching any object or anything. And now nobody should ask me, sir, what about air resistance and all? Be careful now, okay? Unless otherwise specified, and I say it's a free body unconstrained, it is unconstrained. No external force is acting. So it is rotating and also translating. Now you see, let's all understand that. It is rotating and translating. So then it should be rotating about some point.
Yes, sir.
Yes, sir.
It should be rotating about some point, right? And it should be rotating about some point. Okay. Now here you see, when a body is having unconstrained motion, unconstrained translatory as well as rotational motion, then its axis of rotation will always pass through the center of mass.
Yes, sir.
Its axis will always pass through the center of mass. Hello, are you with me?
Yes, sir. Yes, sir.
If a body is translating and rotating, okay, then its center of mass will be passing through its center of rotation will be passing through the center of mass. Or in other words, the body is rotating about the column or center of mass.
Yes. Yes, sir.
Unconstrained, man. That is, it is not touching any other body. No external force is acting.
Yes, sir. Yes, sir.
Yes, sir.
It
is rotating about the center of mass.
Yes, it will be rotating about the center of mass.
Okay, sir.
Okay. So if you ask me justification for that, you see, right now I just discussed that if you give external force to a body, that external force, when we represent it, will be acting on the center of mass.
Yes, sir. Yes,
Now, so it will be acting on the center of mass. That means now the external force which produces acceleration, we will keep that acceleration vector on the center of mass. Correct?
Yes, sir.
Center of mass. Center of mass is a point. Center of mass is a point. And so it will translate. It will translate. Okay. Right? So therefore now the center of mass cannot rotate about itself. Okay, so therefore the center of mass cannot rotate about itself, and only one point supposing I consider this as a planar, only one point in a planar diagram or a planar object will be at rest. What is that point? That point will be the point through which the axis of rotation is passing.
Yes,
Yes, sir.
Yes.
So an unconstrained motion of a body in translation and also rotating, it will only rotate about the center of mass. Is that clear?
Yes, sir.
Yes, sir.
Yes, sir.
See, now you have to start observing and understanding this. Supposing I have a rod. I have a rod of certain mass m, and this is ground. I allow it to fall. I have a rod, I leave my hand. How will this rod fall? Will it just fall like this, or in the process it will also rotate and translate?
It depends on the center of
It will only translate or
Yes.
it will just fall, correct?
Yes, sir.
Why will it rotate?
It will drop, it will move.
Why it will move? See, that's what, no speculation. You should apply science. Okay, so what is happening here? Okay, the acceleration due to gravity is acting at each point.
Yes, sir.
Okay, so all these points will be uniformly accelerated. Okay,
Yes.
so therefore
Yes,
it will
sir.
continue to go. In fact, I have shown one diagram also, no? A pen falling like this.
Yes, sir.
That should be clear. So it will not do this. Now the question is, say now it is falling down, and supposing I have some rigid object here. So what happened? As it is falling, when this edge touches this rigid object, then momentarily what happens? This point will come to rest. Momentarily.
Yes, ma'am.
But these points continue to move.
Yes, sir.
Yes, sir.
Yes, so that is when it touches this point, this will be the diagram. So at that moment what happens? This point will be at rest, everything else will be in motion. And therefore now what happens now? The angle of the rod will now change.
Yes, sir.
Yes.
Correct? The angle of the rod will change. and the angle of the rod changes, it starts what? It starts rotating.
Rotating. Yes, sir.
It
Yes.
starts rotating. Now what happens? What happens to the rod? It will now continue to rotate and also fall.
Well, yes, sir.
Correct?
Yes, sir.
Yes, sir.
Will it happen like that? Think, the rod is falling, tongue will touch this hand. No, you should give scientific reason, not your thinking for thinking here.
So can you repeat what the question?
What happens after it touches this? Will it keep rotating and falling down? Or here only it rotated and then it will have translative motion?
Sir,
The rod was falling, it will hit here. See, it is falling, my hand will touch. Then what happens? The rod will now
Sir.
rotate at that point. That is for sure.
Yes, sir.
It will rotate at that point. Will it continue to rotate and fall, or here only the rod change its angle, then it will have straight
Sir,
point?
only it will change its angle.
It
and
will
fall
only
like
change
that,
the
sir.
angle and
Then it
then
will
fall
have
down.
translative motion. With
So
whatever-
afterwards it will not change the angle.
And it will not change the angle. Once it
Yes.
touches the angle, it will not change the angle again.
It will not change.
No, sir.
What is the basis for your answer?
Sir, when that point hits that rigid support, no, sir, that time it comes momentarily to rest, sir. All the other particles are having they are having their own motion, sir. So after, at that point, sir, if you consider normal force will act.
Normal force will act here only.
Yes, sir, normal force will act there, sir. So it tries to counterbalance the other forces which are acting in the downward.
Why should it counterbalance?
Sir, that normal force is acting upward direction, sir.
Okay, it will balance.
And
So
all-
that force point is acting there, all other
Yes, sir,
points are in
at that,
motion.
at that point it will rotate, sir. Afterwards, when it's not in contact with that rigid body, sir, that time all other forces will be acting same for all the points. Only it will have only translation.
No, you did not apply science. Anybody else?
Sir, can I address this as a
See, I want your answers based on science. You are not. You have to apply science. You have to apply the laws and tell. You cannot give whimsical answers. I don't want your super intelligence here. It should be, who is intelligent? One who has the knowledge and who is applying the knowledge at that instant. Right? And whatever knowledge you are applying, it should be scientific knowledge based on laws. Yes. Okay, tell me. Pratyush, you wanted to tell.
Yes, sir.
Huh.
Sir, when the rod touches the surface, sir,
Hmm.
there is some external force acting on the rod sir, at that moment.
Hmm.
So, sir, also the other part of the rod is in under motion, sir.
Hmm.
And that part is also affected by gravity, sir, gravitational force.
Hmm.
So, sir, when that rod will be falling down, sir, the other part will also lose contact, sir, and at that point, at that instant, again, the force produced by the surface, it will go, sir.
See, you are beating around the bush. See, till that point it is understood that it hits and the body at that moment that becomes the instantaneous axis of rotation and the body will start rotating. Now the question is, afterwards will it continue to rotate or it will not continue to rotate? Yes, at that point the angle of the rod change and it continues to fall down. Is it that, or after that point the rod is continuing to rotate and fall down? That much only you should answer, because see, time is very precious. Yes, anybody else?
So, once the rod hits our hand or anything, we are providing an impulse force, sir.
Mm-hmm.
And due to that, it will start rotational motion, sir.
Mm-hmm.
And there is no other external force that is disturbing the rotation of the body, sir.
Okay.
Neglect air friction, so it will continue to rotate.
It will continue to rotate. There is no other force to stop rotation, so therefore it will continue to rotate. Anybody else would like to add something here? See, I wanted some concept to be used here. Some concept to be used here properly.
Moment force.
Moment of force or moment of force? What is the moment of inertia?
There is external force acting.
See, what is Newton's law based on? What is conserved? When force acts on a body, what is the conservation of momentum?
Yes.
I hope all of you know momentum, correct? No?
Yes.
So momentum, see now the rod is simply falling here, it is simply falling. What is conserved here? See, there are two things. One is, you use the Newtonian laws, okay, as it is, vectors, free body diagrams and all. Other things are the conservation laws. Simple. So when they force acting on this body, see, on this entire rod, the force acting gravitational force, so it will continue to accelerate. That is for sure. The rod will not change its direction. But once it hits it started rotating. Now you should have used the concept of angular momentum. Hello.
Yes.
So the angular momentum is conserved. Because see, only at this instant when it hits, there is a torque applied to the body. When it just hits this body, there is torque applied to the body. Why the torque is applied?
Yes.
Because if you take the weight of the rod down, and this becomes a constraint here, and therefore W into this perpendicular distance will become the torque. And because of that, so the torque tau divided by the moment of inertia about this point will give you what? The angular acceleration alpha. So at this point it will accelerate, and therefore what happens? Its omega was 0, now its omega is non-zero. And nothing is, you will learn, there is no external torque to oppose that motion, and therefore it will continue to rotate and fall. Got it all of you? See, I wanted you to hit that this one now, angular. See, now you see you are dealing with things like this, so you should start now using the right concepts at the right time. Okay, see, this is where your challenges will start now, because you have learned so many things. See, our way of learning still now. So I am dealing with thermal physics, so laws of thermal physics. So I am dealing with this, so only this. The other day I asked you an example of, momentarily the body is at rest, but it is accelerating. A frame, give me the example of a frame of reference where it is momentarily at rest, but it is accelerated. So you started only talking about a train moving, a wheel rotating, your mind was in only because we are discouraging with motions like this. So you are trying to find examples in that direction. So now, थोड़ा हट के सोचने का और बोलने का, ठीक है? So therefore, students, so now you see, in this particular context, what I want you to understand here is that, so when a body is translating and rotating, now if I say there is a particle, so there is two components of velocity, one because of which it is rotating, and another thing it is because of translating, and therefore the total velocity of the body will be the resultant velocity, will be the vectorial addition of these two components. And when you say it is rotating, so about a point it is rotating. And if it is unconstrained, then it is rotating about the center of mass. As simple as that. Is it clear?
Yes, sir.
Yes, sir.
Okay.
Yes.
Okay, fine.
Yes.
Now I used to experiment with a duster and show you, right? Okay, just give me the duster. Okay. So I used to say, like, I have this. If I apply force to this, I am applying force. What happened when I applied force? What happened now? See, now tell me, while I am applying force, what is happening?
It accelerated in the direction of ship. Center of mass accelerates.
Okay, again, I want you to use the right concept here. I am applying force here. I hope all of you can see. What is happening?
Yes, sir.
What is happening?
It is your benefit.
Okay, in this context, what type of motion is this?
Translated motion.
Only translated motion.
Translated. Only pure translated.
It is better that you stress it's only translated motion. Okay. Now tell me when I am applying force.
Pure rotation.
Good. Better improvement.
Yes.
Okay. Now,
Combined.
combined, correct? So, under what condition it was pure rotation? Under what condition it was pure translation? Under what condition it is combined?
Sir, when the force was acting along the line joining of center of mass, then it was the translative motion, sir. And
it was perpendicular to.
Yes. So your two friends who are sitting here are answering. One of them said, if the line of action of the force is passing through the center of mass, it was translating. And when the line of action is perpendicular
to the center of mass, line joining the center of mass. Line.
What is that line joining center of mass? To the point and the line. Yes, when it's perpendicular to the when you draw a line perpendicular to the force and passing to the center of mass. Okay, and then the body will only have rotation. And when these two conditions are not there, then it is having combined. Hello, are you with me? Say now this is a rod. Supposing you apply force here on the rod. Okay. Yes, the entire rod will get the force. But whatever force you apply to this point will have to travel to this point. So this will take a small time, very small time. In fact, it travels at electromagnetic speed. So, but it will take some time. So that means now this point will get more force. I mean, this point will also get the force. But for this duration of time, the force is already acting, and therefore what happens? This rod will rotate and also translate. Okay, so that is how you have to understand. Okay, so that is why you see this rod will have omega here. It will start rotating as well as it will start translating. Hello, are you with me?
Yes, sir.
Yes.
Now I will say this force is a nudge. Nudge means an impulse force. I just tap like this. Tap. Then obviously you see this will rotate and also translate. I have an object and assume my hand is frictionless. I'll do like this, tuck. Okay. And then you see, supposing I keep this duster on a table which is frictionless and I nudge it. Then you can see that on the table this is rotating and also translating. Hello?
Yes, sir.
Yes.
So the same thing, whatever I explained. So therefore, you will have omega and also you will have BCA.
Yes, sir.
So as a matter of fact, since again now the table is frictionless, there is no constraint on it is unconstrained motion. Correct? Hello?
Yes, sir.
Yes, sir. Yes.
Unconstrained motion, and therefore you can expect that body to rotate about the center of mass and keep moving it.
Yes.
So therefore now if you take this particle, you will draw a vector here, okay, and you will draw a vector here. So what is this? This becomes the velocity component because it is rotating, and this component is because it is translating, and therefore the net velocity of this will be this plus this.
Yes, sir.
Yes, sir.
Yes.
Okay, so start getting used to this.
Okay.
All of you start getting used to this. Okay, life will become jingalala.